All right, everyone. Welcome back here. We're going to be jumping into 5.3.2. In this section, we're going to be adding on a new test that is going to kind of go and add to our total list of tests and approaches that we have for dealing with these infinite addition problems. Okay. So far, these are some of the ideas that we have tackled. We kind of see over on the left, we have our types of series that we've kind of identified thus far. And what we've started to see is that very rarely will I come across exactly one of these types of series, but that there are so many different kinds of addition problems out there that sometimes I'm going to need some extra tests. We found this test for divergence in the last section was extremely useful, as well as some other properties of series that we discussed in the theorems there. But today we're going to be introducing the integral test and trying to get a sense of what exactly this test is for and why I would even really need it. Why aren't maybe all of the things that I have up here already sufficient? Okay. To go ahead and take a look at that, let's go back to the notes here, and you can kind of see what we have in the opening motivation. So oftentimes, again, finding the exact sum of a series is really difficult, and that's because when I want to find that formula for the nth partial sum, remember that's our S sub n, that's really fairly complicated to do in most cases. So we're going to take a look here today at what happens in more scenarios where I still can't find that S sub n. So here's a series, as I state, that doesn't have a nice formula for its S sub n, its nth partial sum, and it's this guy. And again, this is a pretty, innocent looking sort of a series. If I was to think about the numbers that actually occur in that particular addition problem, I can see that it's like the number 1 over 1, and then it's 1 over 4, and then 1 over 9, and then 1 over 16, and so on and so on and so forth, right? So it seems fairly innocent. It almost actually looks like the harmonic series, except that it's missing several terms. It doesn't have a 1 over 2, a 1 over 3, and so on. Okay? But maybe I want to know if this series converges or diverges. Well, we're going to take a very kind of strange approach in attempting to determine if this series actually does converge or diverge. So here's the approach that we're going to end up taking. We'll state this. In order to attack this question, we will consider the integral from 1 to infinity of 1 over x squared dx. Now, you might be able to tell kind of immediately where exactly this integral is coming from. You'll notice that in the addition problem, I was working with 1 over k squared, and now I'm going to attempt to integrate 1 over x squared. So I'm going to try to integrate like the matching function. But of course, I note that I do have to convert to a function here. Now, the weird part is, why in the world would I actually care to look at this particular integral? Okay, so here's what I'm going to go ahead and do. I'm going to go ahead and first just try to sketch a picture of what exactly it is that I'm working with here in this improper integral. So if I have my x and y axis sitting here, if I was to sketch out 1 over x squared from 1 to infinity, I recognize that at x coordinate 1, I get y coordinate 1, and definitely this curve decreases over time. So I'm kind of ultimately looking for here the area between that curve and the x-axis going off to forever. Now I'm going to go ahead and state this. Instead of computing this integral directly at the moment, and I know that I have the ability to do that, but I'm going to pause, and I'm going to think about this in a slightly different way. Let's suppose we attack this integral. Nope, sorry, not attack. Suppose we approximate. Suppose we approximate this integral using a left Riemann sum with rectangles of width 1. Okay, so this is a weird thing to try to do, but I could maybe start to figure out roughly what this looks like in the picture. If I was going to start to put in some rectangles of width 1 in here, and I wanted to make them all left endpoint approximations, I could maybe start to create these blue rectangles. So again, like I'd have a rectangle that goes from 1 to 2 as its base, and if it goes up and touches on its left side, I'll get a rectangle that looks like this. Let's call this rectangle 1. Okay? I could do the same thing when I go from 2 to 3, and I can create a rectangle that looks like this. Let's call that rectangle 2. You can see that I could easily get rectangle 3, and of course I can continue to get rectangles 4, 5, 6, and on. I'll just kind of put in here like a blue dot, 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 right? Those rectangles could keep going. Now immediately I might be able to see right away, when I find the area in the blue rectangles versus the area determined by this improper integral, the blue rectangle should have more total area. At least it seems that in the short term right now, they're an over approximation. So I'm going to go ahead and attempt to see exactly what the areas of these rectangles happen to be, and we'll see that we get the following. Okay, so we see that the area for rectangle 1 is equal to, well, let's see, it's 1 wide, and it is as tall as the function is when I'm at x coordinate 1. Of course, that function, when I plug in the number 1, just produces 1. So this has an area of 1. The area for rectangle number 2 is, let's see, it's 1 wide, and it's as tall as the function is at x coordinate 2, which means it's a fourth. So it's a fourth times 1. So that's a quarter. Area of rectangle 3, you might be able to see very quickly, is going to become a ninth. And I could probably start to generalize this to say that the area for, let's say, rectangle I could have a formula. Like, again, if I was working with any particular rectangle. Again, I'd ask you to try to think about this for a moment. What could be a general formula for the area of one of these rectangles? Well, something that you might come up with is it seems like I could really use a formula like 1 over I squared, right? That is, whatever rectangle number I'm working on is the value that gets squared in the bottom. Just like here it was 1 over 1 squared, 1 over 2 squared, 1 over 3 squared. So in general, 1 over I squared, okay? So I could state this. So a formula for the sum of the areas of all rectangles would be, I could make this a summation because I'm going to add up a bunch of areas of rectangles. The general area formula is 1 over a k squared. And I could start at 1 and go to forever. Now, if I look at that, that should actually be really impressive because that series is extremely familiar. That series, of course, is exactly the series that we started with. So what we see is that these blue rectangles in the picture actually represent the series that we're working with. And since I can go ahead and see that these rectangles provide an over approximation for the area under the black curve, I might be able to make the following conclusion. So I'll say since the approximation is an overestimate of the area under the curve, we conclude that if I was to actually evaluate that improper integral, if that integral was evaluated and it's found to be divergent, right, like area under the black curve is divergent, then what could we probably say about all of the area in blue if it must be more area? Well, the answer here seems like it would follow very similarly to kind of like the comparison theorem that we came up with improper integrals, that the larger item than something that's divergent would also have to be divergent. So this is kind of an interesting connection that we're forming. We can see that there is a connection between what does the improper integral do and what does the series actually do. Notice again that both of those things have the same underlying quote unquote function with this 1 over x squared or 1 over k squared. Okay. So this is kind of an interesting thought. We can go ahead though and take a look at what exactly would happen when we actually investigate this particular integral here, and we'll see something maybe kind of surprising. Take a look. I'll state that we note the integral from 1 to infinity 1 over x squared dx. I could actually try to evaluate this. Now I'm going to do this fairly quickly. If you need to, you can pause and rewind the video to take a look at how I am working through each of these steps, but this is stuff that we've dealt with previously. So of course, I'm going to turn this into a limit, and then I'm going to think about actually integrating here. Let's see, I think my antiderivative is negative 1 over x. I evaluate from 1 to t. And I'm going to end up with negative 1 over t plus 1. So it looks like here the improper integral evaluates to 1. So unfortunately, the idea that we had up above, that if the improper integral was divergent, means that the series is divergent, while true, doesn't actually seem like it's going to help us with this particular series. The question that we would now want to ask is, what would happen if we actually come across an improper integral that is convergent? Does that tell us anything about the series? Okay. To go ahead and actually take a look at how we might do this, we're going to try to go ahead and rework the exact same problem again with just a slight modification. Again, I'm going to go ahead and put down a rough picture of what my curve looks like. And I'm going to imagine all the same points kind of existing along my axes. And I'm going to state the following. What if we now approximate the area using a right Riemann sum? Okay, well, let's see. Again, all I'm doing is switching up how the approximation is going to be done. So I'm still going to make the rectangles with 1, but I'm going to go up on the right side and touch the function. When I do this, I get rectangle 1, rectangle 2, picture not drawn to scale, rectangle 3, squeezing in there, and again, kind of a blue dot, 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 that could keep going. Okay, so again, I think I could find each of the areas here. The area for rectangle 1, well, let's see, that would be, looks like 1/4. It's 1 wide, but it seems to be as tall as the function is when x is a 2, which should be 1/4. Area for rectangle 2, I believe, is going to be 1/9. Area for rectangle 3 is going to be 1/16. And I might be able to summarize all of those to again get an area for a rectangle number I. Again, I'd like you to try to think here about what exactly might that formula be? Well, you might come up with the conclusion that it can actually look like 1 over I plus 1 quantity squared. Notice that the denominator has to have 1 added to it first before it's squared. So when I'm on rectangle 1, I have to go to 2 and then square, or I go from 2 to 3 and then square to get these particular values. What's interesting is that unlike in the last approximation, while these values here are similar to the values that are in our original addition problem, they're not perfectly in line with the numbers from our original addition problem. Take a look. Our original addition problem had the numbers 1, 1/4, 1/9, 1/16, and so on. And with our first approximation, We got exactly those numbers in exactly that order. Now we almost have those numbers, but it seems like we've skipped ahead by one. Well, that's not too big of an issue. We could go ahead and kind of state this. A formula for the areas, well, let me say, for the sum of the areas of all these rectangles is, and again, I could state this as I just have to add up all the areas. So this is an addition problem that represents the area of all the blue stuff. Now I'm going to go ahead and attempt to rewrite it here, and sometimes this is an awkward step for people to see, but take a look here at exactly what I'm writing. Now, it might seem kind of strange because I changed the counter variable, but I also changed the formula in the denominator. But I think that even by doing that, this is still the same addition problem. It still produces the same values. It's just a re-expression of the same idea. So notice here, this is still, the first addition problem is working with 1 over 2 squared, 1 over 3 squared, 1 over 4 squared. And so is my new addition problem. But the cool thing is that this looks very, very similar to the addition problem that I started with, except that k is not equal to 1, but k is equal to 2. Okay, so I'm going to go ahead and state the following. Clearly, this approximation is an underestimate of the integral from 1 to infinity of 1 over x squared, right? That is, the total area underneath that curve in black is definitely being underestimated by the blue rectangles. So if it is the case that our integral is convergent, then we will conclude that the series, notice that starts from 2 and goes on, is also convergent. Again, this is very similar to the idea we had with improper integrals. If the big function has a finite amount of area under it, then the smaller amount of stuff could not be infinite. It must probably be a smaller amount. And so we reach this conclusion of it should be convergent. Okay. Now, of course, we haven't quite answered the original question unless we pull on an idea from the last video. Of course, we would see that we weren't interested in this series starting at 2. We wanted this series starting at 1. But if we know that the series starting at 2 converges, we know that the series starting at 1 could be expressed as the series starting at 2, but just with kind of like the first term peeled out to the side. And since the first term here is 1, we can see something kind of convenient. We can see here that 1 is clearly a finite value. This here is a convergent series. So if I take something that's convergent, it adds up to a finite value, and I add 1 to it, clearly I'm going to arrive at something that is also convergent. Okay, so we can see here that we get something really, really convenient. We were able to determine that this series is actually going to be convergent. Remember, the idea is that if you add or subtract, or delete finitely many terms to a series, you do not change its convergence. Okay. So in this case, it seems like we can reach the following conclusion. since this integral equaled 1, we showed that before, then the series is convergent. Notice again, we don't know what it's convergent to, only that it is convergent. Okay. So this is a long explanation of how exactly this new test is working and what exactly it allows us to say. Now, the final thing that I have here before we'll end at least this segment of the video is to kind of recap all of this in the associated theorem, the integral test. There are actually a couple conditions that go along with this test. They were kind of being used up above, even though they weren't specifically stated. But you can probably see that the following restrictions that I'm going to have on the function that we work with are definitely satisfied by the function 1 over x squared. So here's what we have. Suppose f is a continuous, positive, decreasing function on 1 to infinity, and let a sub n be equal to f of n. So again, I want to have this function be the matching function for the actual sequence. And I want to make sure that this function is continuous. 1 over x squared is clearly continuous on 1 to forever. Positive, meaning it's above the x-axis, which our function definitely was. And it needs to be decreasing. Okay. If I meet all of those things, then I can reach one of two different conclusions that we kind of saw above. If the improper integral of the f of x is convergent, then our series converges. And if the integral is divergent, then our series diverges. Essentially, whatever the integral does, the series follows suit. The series does the same thing. One note on this is that in general, we can let a, or not we can let a, how about we can change where our integral begins and therefore change the index of the series. What I mean by this is that there's no reason for us to have these indices of n and the lower bound on these integrals be a 1. In fact, I could update all of this where I replace all of the 1s maybe with a new letter, right, as just some other starting point. I could start at a 4, I could start at a 10, I could start at any possible value. So we can work with an interval, and I'll just say mystery value a to infinity. So this sometimes will be a highly valuable thing that we'll take a look at in some of the examples to come. All right, I'm going to stop this portion of the video here and we'll take a look at some of the examples in the next video.